All right, so on this lecture, we're going to try to finish chapter 13, and that'll be it for the coverage of the material for the exam. So so remember, exam 1 was chapters 10 and 11. This exam will be 12 and 13 for the coverage. Okay, so for review, we looked at on lecture 24 the current blocker, which is the same thing as AC current bypass, right? Where you have this current that has a DC and an AC, and this is sort of like a divider where the DC has tendency to go down this path of resistance, and the AC has a tendency to go down this path right here. You can convert these currents to voltages through transimpedance amplifier. We also looked at the equivalent voltage-controlled current source and current-controlled current source of the hybrid pi model. Okay, so the hybrid pi model, remember, was when the current source right here, the voltage-controlled current source, actually had zero gain, so that's gone. So you can have it like this, which is a voltage-controlled current source, or you can model it like this, which is a current-controlled current source, or you can get rid of the output resistance right here if that is negligible. And in this lecture, toward the end, we'll figure out when you can and cannot get rid of that output resistance. Then we look at the small signal BJT model, and we've found that it's pretty much like our analysis we did for the diode. And as long as you could linearize around a point, but you only have like a small range to linearize, right? So as long as you're within that small range, then you can have a really good model just based on a straight line equation, a straight linear equation, even though over the entire span it's definitely not linear. And also we looked at the terminal voltage and input resistance. We'll continue more on that today, too. So for our very last lecture, we looked at signal source voltage gain, okay? And we looked at design guides for common emitter amplifiers. We looked at the upper bound for common emitter gain and small signal limit for the common emitter amplifiers here. And we compared MOSFETs for the transconductance, output resistance, and intrinsic voltage compared to BJTs for its transconductance, output resistance, and intrinsic voltage gains. And we basically use this as our analysis. So you start off with the overall transistor type of model. Then you do your AC analysis, which means you're going to have some DC current blockers and some AC current bypasses right here. So that gets you from this to this. And then to go from this to this, you convert this to a small signal model where you replace this with this piece right here, the output resistance, and a voltage-controlled current source. And then you group all these together and then call that your load resistance. Okay. So for today, we're going to cover the rest of these things. These are subsections. So we're going to look at, do a summary comparison of the small signal models of the BJT and FET. We're going to look at the common source amplifier, look at the common emitter and common source amplifiers, do a summary of that, and then look at amplifier power and signal range. Okay, so just for summary, here are, I'm not going to say all the terms, but a lot of them. So a lot of these things came from Digitron, right? But they were reintroduced here in this class. So we have the transconductance amplifier, the capacitance per unit area across the oxide, electron mobility, channel width, channel length. This VTN, which we'll see again, is a threshold voltage for the formation of the inversion layer. Lambda is the channel length modulation parameter. VA is the early voltage. We'll see that. ID is drain current. IC is the collector current. VBE is the voltage between the base and the emitter. VDS is the voltage between the drain and the source. This IDSS is the current saturation current. VP is the pinch-off voltage. This VGS is the voltage between the gain and the source. VT is the thermal voltage. K is the Boltzmann constant, T is temperature, Q is the magnitude of a single electron, B0 is a small signal current gain, BF is a small signal voltage gain, R0 is the output resistance, R pi is the input resistance. And we'll see another one of these today. Like we'll look at different versions of this input resistance and output resistance today. UF is the intrinsic voltage gain, and GM is the transconductance. Okay, so here's a summary of a few of the things that we've seen already. So right here is the parameter. So we have the transconductance, input resistance, output resistance, intrinsic voltage, and the small signal requirement. Okay, so this column right here is for the bipolar transistor, BJT, and here's some FETs right here. Here's the MOSFET, and here's the JFET. So a few things that you can see right away for the, like for example, the transconductance, you can see that is pretty much linear with respect to this collector current right here. For the MOSFET, it's this ratio right here where this is the drain current. But this right here is, for room temperature, this is pretty constant value. But this right here also depends on this range between these two voltages. So you have a little more play here. And same with the junction filter effect transistor, similar type of form. For the input impedance for the bipolar, it's like this, which is very small in comparison to the MOSFET and the JFET, which are nearly infinite, comparatively. For the output resistance, looks sort of like this, where you have the early voltage over the current, the collector current, and these two forms right here are the same for the drain currents. For the intrinsic voltage gain, you have the early voltage over the thermal voltage. So both of these are constant. So this is invariant to other parameters. But for the MOSFET and the JFET, they can vary greatly. Here's a small signal requirement. So the voltage between the base and emitter has to be less than 5 millivolts. For this right here, you'll see this in the lecture right here. It's like 20% of the difference between these two voltages right here for both of those, with that and also the pinch-off voltage. Okay, so it's like 20% of that voltage difference. So so that's pretty interesting, right? So you want to use these, you want to consider those kind of things when you're looking at design. Okay, and also this right here is for the DC IV active region for these values right here. So so let's look at the common source amplifier. All right. So and what we'll do is we'll analyze the small signal characteristics of this common source CS amplifier. So sometimes you'll see C as being common. Other times you'll see C as being collector. Okay. So this particular common source amp, it has this enhancement mode in channel MOSFET, where this VTN is greater than 0, right there, and it's in this 4 resistor bias network right here. So first thing you do is you do your AC, right? So these become bypass, for, DC current bypasses. I'm sorry. These become DC current blockers, and this becomes an AC current bypass. So that's why this right here becomes shorted. This right here also becomes shorted to here. This is bypassed for the current. For the current. So you don't see this RS here any longer. And also the voltages, the DC voltages, they become grounded. So that's why these two are now in parallel, because they're both going to ground from this node right here. Okay, so that's the first step. Then the next thing you want to do, you want to replace the transistor with your small signal model. So you're going to take this piece right here and then replace it with this right here. So that includes the voltage control current source and the output resistance of this right here. the RD and R3 are still the same. Okay, but now all three of these in parallel become your load resistance. Okay, and so that's what this is right here. So just replace that with your load resistance. Okay, so so the input signal is applied to a transistor gate terminal. The output signal appears at the drain, and both the input and output signals are referenced to the common source terminal. Okay, so basically that just means that your input and output, they're all referenced to this common reference right here. Okay, and you can see that here, back here, is hard to see, right? That your input and your output have like a common reference, but here is much easier to see. Okay, so at this stage, the small signal model of the MOSFET and BJT, they're virtually identical except for this R-pi, the input resistance. As you can see here, this is for the MOSFET and this is for the BJT. And the biggest difference between these is this piece right here, right? So you have your R-pi here, and this looks like an open circuit right here. But everything else is the same type of form, right? You have your load, you have your voltage controlled current sources, okay? You have your inputs, right? Yeah. So, but there's a few differences in the labels. Like this is VB, that's VG. This is the drain, and that's the collector. But other than that, same forms. Okay, so let's look at the common source terminal gain, the terminal voltage gain. Okay, so that's going to be defined as this right here, and we looked at this type of thing last lecture, but basically that comes from this right here, right? So you're just taking this V out, which is equal to this, and you're going to plug that into here, and then the VG cancels out with that, and then you're just left with this. So 180 degrees out of phase, and it's proportional to your RL, or your transconductance. Okay, so for the overall gain, for the common source signal, the common source signal source gain, that's this right here, where this is V out over V in, so it's a V out over V in, and then you take these two right here, and then you multiply it by 1, but this is going to go on the numerator here, that goes in the denominator, okay? So this right here we saw last time, which is equal to this, and this right here is done by voltage division, so that gets plugged in there, and this is your expression you get. Now, if your Ri right here is much, much less than this, then it becomes negligible. So you could think of it as this type of system here, right? Where the voltage across here is the same as the voltage across here. So it's like your VG is equal to your VI. Okay, so that's what this is. Your VI is equal to your VG right there. And that's what that is. Okay, so a design guide for common source amplifier. So when using a resistive load with a common source amplifier, it is often tried to achieve, you want your R3 to be much, much greater than your RD. You want your R out to be much, much greater than your RD. Okay? So the total load resistance on the collector of a transistor is basically just RD, because the other ones are quite negligible. So the signal source gain can be written like this, which you just seen in the last slide, and you can extract it to like this. So this transconductance is your ID over this, right there. Now the ID part, that represents the DC voltage drop across the resistor RD. And this voltage is usually in the range of 1/4 to 3/4 of the power supply voltage. Okay, so if you're assuming that your ID/RD is about equal to half of your VDD, and this difference between VGS and VTN is about 1 volt, then you can express it like this, where your gain is just negative of your VDD. So that's an approximation. But these kind of things are used when people design these kind of things. So if you're assuming for the small signal limit for the common source amplifier, if you're assuming that your VG is much, much greater than your RI, then from this right here, you could just solve for this. Your VI is equal to this VGS, where you invert this fraction right here. If this is much bigger than that, then this fraction right here becomes about 1, and so that's just equal to your VGS. Or like we've seen in that table, that your VI is less than 20% of the difference between those two. Okay. All right, now let's look at Rn of the common emitter and common source amplifiers. Okay, so it says here that the voltage gain of the MOSFET amplifier is much lower than that of the BJT. However, a small signal can be much larger for the MOSFET than for the BJT. And the impedance of the MOSFET is larger than for BJT. We saw that from the tables. So this right here is the input resistance definition for the common emitter amplifier. Okay, and this is what we're talking about right here, the input resistance, as seen from this point. And here's the input resistance definition for the common source amplifier, right here. Okay, and I found this online. It's like another way to think about this common concept. So it says, so one way to tell if the transistor is a common source, common drain, common gate, or common emitter is to first recognize where the signal enters and leaves. Okay, and then the remaining terminal is what is known as common. For example, signal's coming in this way, and is leaving through here for the output. Okay, and through AC small signal analysis, this is going to ground right there. It's like an AC ground right there. Similar here. So it's going in through here. Here's the output. Here's your AC ground. Okay, so common emitter and then common source amplifier. So for the common emitter amplifier, what we'll do is do our AC equivalent circuit. So these become DC current blockers. This becomes an AC current bypass. So this right here becomes this. Okay, and then for a small signal model, you take your transistor right here and replace it with the voltage controlled current source and your RO. So both of these come from this right here. And then, so once you have this, then your input resistance is just found as this. So it's seen from over here, but it's just your Vx over your Ix. So here's your Vx, here's your Ix, it's a ratio of that. And as you can see, that's just this RB and RPi in parallel. Okay. And that RB right there was from R1 and R2 in parallel from the reduction we did previously. Okay, so that's your input resistance for that. Okay, so for the common source amplifier, so this was the common emitter. For the common source amplifier, this, doing an AC equivalent circuit, becomes this. And the same thing again, your DC current blockers and your AC current bypass right there. And then you take this and you replace it with your voltage control current source and your RO of that. And then, so what you have this right here, you can see that your input resistance is just found to be Rn is equal to Rg. That's just remains right there. And that's just your open branch right there. Okay, so still the ratio of Ix and Vx. Okay. All right, so for this common emitter amplifier, let's look at R out. So R out is seen from this side over here. Okay, so we'll do the same thing. So you do your AC equivalent circuit, and then replace this with these two. And then your R out, as seen from over here, is your Vx over Ix, your Vx over Ix. And that's just RO in parallel with RC. And the reason that you're not considering this right here is because when you're looking at it from this side over here, nothing is causing any current to flow through here. So that means that your VBE is 0. Okay? If that's 0, then this is off. So there's no current going through here. So that's why you're only looking at these two in parallel compared when you're looking at resistance from the outside over here. Okay. And you can also do your KCL to validate that. Okay, so for the common source, you do your AC equivalent going from here to here, and then you take this and do your small signal model, convert this to these two elements right there. And then from that, you are looking from this side, your resistance is just Vx over Ix, and it's this R0 in parallel with Rd. And this, by the same argument, there's nothing driving the voltage, any current through here, so this VGS is 0 from this model. Okay, so that's why you're not including this as part of your current flow. Okay, so let's look at some example comparisons between these types of things. So let's just say you have this very similar Q point values. So for the BJT, the MOSFET, and the JFET, here's the Q point values. And they're pretty much the same, okay, in terms of currents and voltages. But if you look at the overall amplification of these, the gains, you see that there's quite different. This is like around 160, this is around 10, and that's 20, right? For the intrinsic voltage gain, this is pretty much constant, stays around 3,000, but these can be slightly different. And here are like rule of thumb estimates for these values right here. Okay, and here's a comparison of input and output resistances for the BJT, the MOSFET, and the JFET. What you want to take away from this is you can see the R pi quite different. This is 10 kilo ohms, and it's nearly infinite for these right here. Your outputs are nearly the same. These are nearly the same, and also the output resistances right here are nearly the same too. Your inputs vary greatly. It goes from 9K to 1 mega ohm. Okay, and same with these resistances right here. It goes from 100K to 1 mega ohm. So those are some typical values. So let's look at common emitter and common source amplifier summary. So for the terminal gain right here, for the common emitter amplifier, we have this. For a common source amplifier, we have that. So those are the same. For rule of thumb estimates, for this right here is like 10, like an order of magnitude greater than your VCC. And for this right here is just your VDD that you're applying. For the voltage gain, same with both of them. For the input resistance, you have RB in parallel with R pi. Over here you have RG. For the output resistance, you have this right here compared to that, same kind of form. And for the small signal limit, this right here is 5 millivolts, and this right here is 20% of the difference between those. So much greater variability right there. Okay, so let's look at some guidelines for neglecting this RO, which we talked about. So, so it says here that the transistor's output impedance does not greatly affect the above results. So the question is when can you neglect this RO? And it depends. Okay, so so RO must be included whenever it does make a difference, and when it does not make a difference, is when when this gain right here is much, much less than your intrinsic voltage gain. If that's the case, then you could always neglect RO. But if your input or output resistance is similar to or much larger than RO, then you may need to include it. But the book didn't say that that's a definite, but it says you may need to include it if you have that case right there. And some ways of simplifying RO, you can write it either like this, which is the early voltage over the collector current, or 1 over lambda ID right here. A couple of ways you can simplify that. Okay, so let's look at amplifier power and signal range. Okay, so we already saw that the selection of the Q point affects the value of the small signal parameters of the transistors, and hence affects the voltage gain, input resistance, and output resistance of both the common emitter and common source amplifiers. For the FET, the Q point also affects your VGS. But in addition to these kind of things, the Q point choice also determines the level of power dissipation in the transistor and the overall circuit. And it also determines the maximum linear signal range at the output of the amplifier. And we'll take a look at both of those right now. Okay, so let's look at power dissipation. Okay, so static power dissipation can be determined from the DC equivalent circuit. Okay, and that's this right here. Okay, so power supplied by the DC source is dissipated in the resistors and the transistor. Okay, so this power dissipated PD in the transistor is a sum of the power dissipation in the collector base and emitter base junctions. So we're talking right here and here. So here's our PD, right? And power is just your voltage times your current, right? So you have this V collector base right here, that voltage, multiplied by the current passing through that right there. And also VBE and the sum of the currents passing through that, which is your IB, and also this IC coming in here. So both of these two currents right here must equal this right here. And here's your VBE, okay, just by KCL. And then what you can do, you can collect these out and factor out this IC. So that's what that's all about right there. Okay, so this is your power dissipation through your transistor. Now, the power supply, the power that's being supplied to the whole thing is this VCC times your IC and your I2. So here's your VCC right here, and then the sum of the currents going through this voltage is your IC and your I2. Okay, so that's what's the power that's being supplied to the whole thing. Okay, that was for the BJT. Now for the MOSFET, it's very similar. So the power being dissipated through the transistor right here is your VDS times ID right there. So here's your ID, and the VDS is across here. Also, you're adding to that your VGS and your IG. So this right here and this IG coming through here. But of course, this right here is 0, so you're just going to reduce down to V, DS, and ID. Okay, and the power that's being supplied is this VDD and the currents right here. You have your ID and your I2 for the supplied currents. Okay, so the last section of this chapter is signal range. Okay, so there's also a relationship between the Q point and the amplitude of the signals that can be developed at the output of the amplifier. Okay, so for example, let's let the collector and emitter voltages at the operating point or Q point be 5.9 volts and 2.1 volt. Okay, so we're talking like 5.9 right here and this 2.1 right here. So then the difference are the collector emitter voltage, VCE, at the Q point will be about 3.8. Okay, so because the bypass capacitor at the emitter forces the emitter voltage to remain constant, the total collector emitter voltage, VCE, is this right here. And we're talking about this voltage down there, right? So this VCE is your DC component plus the sinusoidal component right here. And here's the magnitude of that sinusoid coming through here. Okay, so for the BJT to remain in the active region, the collector emitter voltage, VC, it must be greater than the base emitter voltage, VBE. So you have this first constraint right here. Okay. So the amplitude of the signal at the collector must satisfy this constraint. So here's your magnitude of your sinusoid. That has to be less than your DC minus your VBE, which is about 0.7. Okay. Now this magnitude must also be smaller than the voltage drop across RC right here at the Q point. So therefore, your magnitude of your sinusoid has to be less than or equal to the minimum of either these two things right there, right? This voltage drop across this, your RIC, okay, or the difference between that right there, okay? So the minimum of either of those. And then if we want to continue this for the MOSFET, to remain pinched off, your VDS must remain larger than the difference between these right here. So that's what this is all about right here. So your VDS, which is equal to that, has to be greater than or equal to this. Oh wait, this is supposed to be capital, so this is DC. Sorry about that. I'll try to fix that. And the signal amplitude cannot exceed your DC voltage drop across D. So for those two things right there, now you have your constraint on your magnitude. So it has to be less than or equal to whichever is smaller, your ID, RD, which is the voltage drop across that, or this right here. Okay. All right. So good, we finished a little early. So any questions about this last part of the chapter? Okay, great. Okay, so what I'll do is I'll get out the practice exam to you guys sometime tomorrow, early tomorrow, and then we'll meet back here Sunday at 3 and then go over that. So see you guys on the weekend.